please.
Okay. Yeah, I've done it, ma'am. I'll now share you the presentation. Sorry to all, and I'll make it up for tomorrow in the best way where I can give you the best things connected.
We know, sir. We know, sir. You can start the recording, Jay.
So today I will talk to you on interesting part of security because we are talking about data, we are talking about face detection, security is everywhere. So I said I'll be touching on two things related to security. One would be with respect to face detection, and the second part I would look into is where the context of the environment is looking like the situation is not secure. I will touch on the first part of face detection. See, this is a very interesting problem. Reason is now today we are talking about the data that is going to come from images and cameras, but the faces that we are looking for have got different information to convey. For example, if you look at each of your faces, it will try to convey an expression. It would also try to convey saying that you are so and so person or you are the same person or not. So the question here is like we are interested in detecting a face of a person to conclude that there is a need for security or not. Ma'am, are you able to see the screen? Hello.
Yes, sir. Yes, sir.
Seen, sir.
Right. So what we will do in today's session is we will walk through the concepts. I'll share you one code also. You can parallelly run the code and you can put your face, which is part of your photo, and check whether your face is detected correctly or not. Right. So that's a plan for today's session. So why face detection? It is a very important way to know that the face can be an identity for a person. But the problem with face detection is like people come with different textures. People have different variations in face. For example, if you look at faces of Asian people versus the faces of people who are in abroad, especially you take Chinese for example, or from somebody from Japan, their eyebrows and the eyes together will not be very much separable. So you can see closed eyebrows regions closer to the eye region. So the challenge here is like how can you detect face and how can you recognize a face? So for this, there's a lot of approaches that has come up, and the simplest approach would be is like go for the pixel level comparison. But the other advantage you can take is you can look for approaches which has got feature detectors. Because yesterday I told you that we can actually use feature detectors to detect the features of the face, right? So if you're going to go for a feature detection approach, then you will have to come back to the metrics and start asking yourself which metric is suitable for me to conclude that my face detection is working correctly or not. So there the answer is very simple. If you are able to detect the certain number of faces in the given image and you are able to divide it by the total number of faces that exist in the picture, then you can conclude that the detection rate is high or not. And irrespective of any algorithms, please always take these participants. You can use machine learning, deep learning, transfer learning, whatever it is. You should always make sure that the number of false positives is getting reduced. So the conclusion is not the algorithm, the conclusion is the false positives. If the false positives have got reduced in your problem, then you can always conclude saying that your approach is the best approach. So you need to achieve a good false positive rate. It should be as low as 10 power minus 6. So you are actually looking for a system in face detection which can do two things. One, it can do a high detection rate. That means if your face appears in front of the camera or group of people appear before the camera, it has a high detection rate. It should also be able to come back and say that it is giving you a low false positive rate. So if you look at this example slide here, where you see different faces of people who are there, like this is something similar to a group photo, where each one of us would be part of a group photo somewhere. So here, if you ask yourself what a detection rate is, it says the number of faces that are being detected. So how many faces are detected? 1, 2, 3, 4, 5, 6, 7. Out of the 7, one is a misclassified one. You can see here. So the number of correct faces that are detected are 1, 2, 3, 4, 5, 6. So the numerator you will have 6 faces, and denominator you will put up the total number of faces that are there in the image. So the total number of faces are 3, 4, 5, 6, 7, 8, 9. So the detection rate is 6 by 9. The second is false positive rate. What is false positive rate is how many false positives have occurred out of the total number of window regions. So the total number of window regions that has come up here is 1, 2, 3, 4, 5, 6, 7. Out of this, one of this is a false positive here. So you have your answer as 1 by 7. So the false positive rate is 1 by 7 into 100. So any system that you are looking for face detection should actually do two things. One, it should actually do a detection rate, and it should have a false positive rate. So you should have high detection rate and you should have low false positive rate. Okay. Now let's look into the possibility of understanding the detection problem here. 1 second. Yeah, there are a lot of approaches for it. So one possible approach is the Euler-Jones approach. This Euler-Jones approach is actually a very famous method. Reason is it has proposed a detector called as Euler-Jones detector. So there are generally 3 steps in Euler-Jones approach. The first step is called as finding the integral image. The purpose of integral image is to find the features from the given image. The second is use an ADABUS classifier for face detection. And next is have an attentional cascade for false rejection of non-face subwindows. The reason is we have been saying that face detection is a possibility to detect the face, but we do not want non-face windows. If we can eliminate all the non-face windows, naturally our face detection approach will work perfectly. So let's see how your Euler-Jones approach works. Now, if I ask you a question, how much is your detection rate here? Your answer would be like you would say the detection rate corresponds to the total number of faces. So you have 4, 5, 6, 7, right? So the total number of faces that has been detected is 7 here. And when it comes to the false positive rate, you would actually look for the number of false positives. So it is 3, right? 3 divided by the total windows. That means 4, 7, 10. So 3 by 10 will be your false positive rate, right? Let's see your Euler-Jones method. How does it work? It's a very interesting concept. In fact, many techniques have come for face detection. But still, even now, the popular technique for face detection, especially where you want to detect faces in any department, it can be in criminology department, for example, also, Euler-Jones is the most successful one. So in Euler-Jones approach, the first approach is you need to use filters, which are rectangular filters, for extracting the image features. So the possible rectangular filters are, there are generally 4 variants of filters. So what is this filter? If you recall the yesterday's session, I told you that if I have an input image, I can apply a convolution operation with a filter and I can extract the features of the image. Similarly, Euler-Jones also gives you filters, but it gives you 4 types of filters, right? So the first filter is labeled here as A, second filter is labeled as B, third filter is labeled as C, fourth filter is labeled as D here. So the rectangular feature value can be given as the number of white pixel values in the white area and number of pixel values in the shaded area, right? You have to find the difference between these two. Let's see how we do this here. If you take an image for understanding, an image has got pixel values for gray levels that you can see here. So the values are seen very nicely for your reference. Now we are interested in finding the rectangular feature value. What is this rectangular feature value? Sum of pixel values in the white area minus the sum of pixel values in the shaded area. Now let's come into this part. So here you can see there is something shaded, rest of it is all white area here. So now let's take the pixel values in the white area. What are the pixel values in the white area? 8, plus 7. Pixel values in the shaded area is what you see here, which is 0 and 1. So it is 8 plus 7 minus of 0 plus 1. So here you get 15, here you get 1. So the rectangular feature value is 14, right? So this is how you can find the rectangular feature value. Now let's take through this one here. Now again, in similar line, we have a box here. We need to find the difference. So what would be the difference? If you all try with your own place, you would say the pixel value in the white area is 4 plus 8 and pixel value in the shaded area is 6 plus 2. So you would get it as 12 minus 8. So you get your answer as 4 together, right? Now somebody would ask a question, what would you do if you want to have a feature extraction? Just conventionally on the given image using this approach. What is the approach? We are able to get the rectangular feature value. Now, if we are going to take the rectangular feature value alone, can we actually do a face detection for it? Yes, let's see how we do it here. If you write an algorithm approach for it, you would say that every time I will find the value of f. So if the f value is large, then I will call it as a face. And if it is greater than threshold, then I can assume it is face, right? Similar to saying f is large. Else, I will say it is not a face. So on the given image, once I get the rectangular feature value, I can say this is not a face because it is not falling above the threshold, right? Whereas this is a face because it is falling above the threshold value. Now, what we have seen right now is Euler-Jones has taught us right now saying that, okay, you can get the rectangular feature value, but Euler-Jones came up with the next step of saying that you can calculate the integral image. What is this integral images? It is the sum of all pixel values which is above and to the left of x comma y. So this x comma y is a pixel reference position. So I want to take all the pixel values which is above and to the left of x comma y, right? So let's take an example for our reference. Now this is an example here of pixel values on the given image. It's a face, for example. Now I would like to do the integral image process. What is integral image? Sum of all pixel values above and to the left of x comma y, right? So the pixel that we are taking for reference is p. So what is the position of p here? Position of p is x value is 3, y value is 2, right? X is 3 and y value is 2. Now my integral image formula says what? Take all the pixel values which is above and to the left of x comma y. So I have to take all the pixel values which is above and to the left of p. So what are your values? 1 plus 2 plus 3 plus 3 plus 4 plus 6. So you would get the integral image value as sum of all these values together. That means it becomes 6, 9, 13, 19, right? Now I would like to find the integral image with respect to Q. So what's the concept? Take all the pixel values which is above and to the left of this, right? When you take above and to the left of this, you should always understand that you should take from the topmost corner, right? So your topmost corner is what? 1. So you start summing up from here saying 1 plus 2 plus 3 plus 3 plus 4 plus 6 plus 5 plus 2 plus 4 plus 0 plus 2 plus 3. This gives you the integral image value for Q, right? So when you are trying to find an integral image, you are trying to actually sum up the pixel values, right? Either along the row, right? And from there you are trying to find your integral image as what we have told you. And whatever may be the size of the image, it's not an issue. You can find the integral image for it. And please understand all these algorithm steps are very important. Reason is, if you are a researcher, you should be able to come up tomorrow saying that I'm using a Euler-Jones for face detection. I have modified Euler-Jones by proposing something. What may be the proposed one? A research guide would always say that, okay, there are 4 filters that are suggested. Can you come up with a 5th filter that can be contributing to the Euler-Jones? Right? So you should know the thought process behind why we have filters for integral image, right? Okay, let's come to the next part. Now, the next is for an entire image, we need to find integral image for all the regions in the image, right? So if you take an image, for example, I assume a rectangle, I mark the rectangle ends as A, B, C, and next is D, right? All the four values A, B, C, D corresponds to the corners of the rectangular region. And all this four is what? I have found the integral with respect to A. That means from the top I summed up. Integral with respect to C, from the top I summed up. Integral with respect to D, from the top I summed up. Integral with respect to B, from the top I summed up till B, right? So I have four values. So the sum of the image would be given like this. So the formula for the area is given as A minus B, right, minus C plus D. A minus B minus C plus D. This will be the sum of the image values inside this rectangular region R, right? Now, if all these four values are found, right, then all you are supposed to do is you are supposed to find the regions together to find the face features. So how do you find your face features? Now comes the next question. You look at a face. What is our thought process of a face? Okay, we have two eyes, we have one nose, we have one mouth, right? God has given us a good face, each one of us. Now, if you look at your eye region here, you will say that your eye region is marked with left eye, right eye, nose, and next is your mouth. What you see in representation is what? All these are filters. Please understand here. So we said there are four types of filters that are proposed with respect to Euler-Jones. The filters are here, right? Okay, so diagrammatically we are suggesting suitable filters for each portions on your face. Eye, nose, and next is mouth. Okay, now when I want to take with respect to left eye, right, I would be interested to find the area with respect to A, right, minus the area with respect to B. When I want to find with respect to nose, I would take the area with respect to C, area with respect to E, okay, right, and I would try to subtract it with area of D. Next, when I take it with respect to mouth, I would take the area of F plus area of H minus the area of G. Simple thought process is like this. You are summing up all the white pixels and you are finding the difference from the black pixel region. So for an example, white pixel regions here is what? C, E, right? You sum up. Minus gray pixel region is what? D. So you say minus of area of D, right? Now, people sometimes will ask a question, see, or a common thought process, how big should be this filter? Because somebody's face is small, somebody's face is big, like that. No, don't worry about that. Whatever may be the size of the face, every image is going to be converted to an image size which is fixed, right? So there, irrespective of the resolution, your integral image features will be able to extract the portions of your face. Now, let's look at this example here. If I take a face image, right, and we apply a filter, right, now we have the shaded area, we have the white pixel area. So how would you do here? You take all the values of the white pixel area, which is what? 216 plus 102 plus 78 plus 112, 29 plus 210 plus 111. You take all the values from the black pixel area, 10 plus 20 plus 4 plus 7 plus 45 plus 7, right? You find the difference of it. So it's 846 minus 93. Answer is what? It is 753. So what is your answer here? If I have a feature value which is greater than the threshold, right, then I would call it as feature I have found is 1. Otherwise the feature I have found is minus 1. Now, this is the next one here to sum up whatever we have seen right now. Now, I have an image. I have set of pixel values. I would like to find the area of each of it. Area of D is what? It is just 1. All right. If I take area of B, the area of B is what? You take all the left pixels, 1 plus 2 plus 3. Right. Now come to area of C. Area of C is what? You would take 1 plus 3, right, which will be 4. Now you take area of A. It is what? It is 1 plus 2 plus 3 plus 3 plus 4 plus 6, right, which is 19. Similarly, when you take area of E, it's what? You go to the top left and see here. So it is 1 plus 3 plus 5. Area of F, you will have to take all these pixel regions, right? 1 plus 2 plus 3, 3 plus 4 plus 6, plus 5 plus 2 plus 4, which will be 30, right? Now, when I want to find the region of the rectangle, what is this? This is the region of the rectangle, right? So what's the formula here? I'll have to take F minus B minus E plus area of D, right? So this is similar to the formula that we have just seen just now, right? So here we have told you very well clearly that if you mark the rectangular region, there's A minus B minus C plus D. In similar line, if you take a pixels of the image to be available, now you found the area for F, you have got for B, or for E plus area of D. Just sum of it, you get the area, right? Now you know how to find the area of rectangle region, which is part of a face image, right? Now, we said there are rectangular features being available. So the possible rectangular features that are available is like this. It's a 1 cross 2. It's a 2 cross 1, right? Because you see one column, 2 rows, right? Similarly, 1 cross 3, 3 cross 1, 2 cross 2. So all these are possible rectangular filters that has been suggested. You can also, in your research, if you'd like to come up with your own rectangular filter, that is also possible, right? And question next, people sometimes face can be very varying. Somebody may have a big face, somebody have a small face. So whatever it is, as I told you, you can actually look at the rectangular features. So the rectangular features is going to give you features corresponding with respect to the white rectangle and shaded rectangle, right? And whatever may be your face size, no, the feature dimension is not going to vary, right? Because whatever is the size for a white pixel region, the same is the size with respect to the gray pixel region, right? Okay, so you need not worry about faces being of different sizes, right? And next, this is just a small example where we say that we have got different possible rectangular features. Label the type of features. So here somebody would say this feature is a rectangular feature, and when you look at this is also a rectangular feature. This just for the understanding part. So next, which I also want you to see is the challenge generally with respect to detection of faces. If you write a generic algorithm using this Boiler-George, we would actually have a sub-window. Sub-window is nothing but the region of interest. So we will have a sub-window. So the sub-window can be of a size of 24 cross 24. So we would try to search within the image, which is of a certain size. So it is 1024 by 1024 is the region we want to search. So we would have X and Y values between 1024 to 1024. Then X comma Y, we'll set it to the top left corner, right? And we will try to have different scales of features. And with that, we can be able to search over the entire image. Right. So possible solutions people have suggested is you can have classifiers, and here I am suggesting for people to use boosting classifiers. In fact, in state of research, I think people know very well that we got supervised learning, we got unsupervised learning, we got boosting classifiers. And why boosting classifiers in deep learning is also is like wherever your problem, irrespective of the data set, people talk about cancer data set or any generic data set, if your problem is going to have outliers, there you can analyze your outliers using boosting classifier. There you can actually go for an AdaBoost classifier. AdaBoost is really an excellent classifier for people to work. So what AdaBoost classifier says is it says that I will give you weak learners, right, through which you will be able to learn the features. So possibly when you combine more than one weak learner, the generic statement you would say is you have created a strong learner. That's a concept, right? So a weak learner is what? It's again a hypothesis. As you can see here, h suffix t of x is going to be 1, right? If p suffix t, f suffix t of x is less than p suffix t, delta t, right? Otherwise, we say it is -1. So it's a hypothesis statement, but it falls into a weak learner, right? So if you now relate it to your image processing problem, here it is in face detection, we would say this is your window, this is a value of the rectangular feature, and this will correspond to the polarity, right? Because we have two types of polarity. Here you can see it is again a rectangular feature same as this, but here it is white and shaded and white. So this is +1, this is -1. So this p suffix t indicates a polarity that we want to indicate, and theta t will indicate your threshold, right? Theta t will indicate your threshold. Now, once you want to use the face detection approach for AdaBoost classifier, so what you can actually do is you can collect faces. There are a lot of face images there, and here people will always suggest that you should build your own data set. So what I suggest and request to the people is also here in the participants is please build your own data set for faces, and that can be very useful when you start working on research related to face detection as a security relevant problem, right? Now, when you want to use boosting with respect to face detection, so what is being suggested by the Weiler-Jones paper in 2004 is they say that you can have hypothesis, and you can have hypothesis indicating for a face and for a non-face. As you can see here, you can build multiple weak learners, and using that you will be able to give a strong classifier which will say you have been able to identify a face or it is a non-face region, right? Okay. So it is shown also in research that you can actually have boosting classifiers and you can achieve up to 95% detection rate and a false positive rate of 1 out of 14,084 samples, right? So as I told you, false positives are very important, and minimizing the false positive is a research challenge, right? So more on it, you can see it under this URL here. Okay. So the next process that is suggested in Weiler-Jones is, can you have an additional cascade for rejection of non-face subwindows? So when you say cascaded classifier, right, people suggest that it is cascading of multiple classifiers. So there, if I say I'm using classifier 1 and classifier 2 of two different types, so what you have built is something called as a hybrid classifier. Please understand in research perspective. If I have classifier 1 together with classifier 2, which are different, there what you have built is something called as hybrid classifiers. When you say cascaded classifiers, all classifiers will be of same. As you can see here, it's like a pipeline model where you have AdaBoost classifier 1, the result is given to AdaBoost classifier 2, then given to AdaBoost classifier 3. The advantage is the amount of error will get reduced when you go from one classifier to other classifier in the cascading process, right? So to handle the false positives, what is being suggested is like you can have many AdaBoost strong classifiers. So the advantage would be is most of the non-faces will be rejected at the first stage itself, right? So number of non-faces will be getting rejected here. Again, it will be more rejected here. Again, it will be more rejected here. Finally, you will have a model which will say that you give me a face image. I can immediately find out the face with a high quick detection rate, right? Okay. So as you can see here, there are multiple AdaBoost classifiers. So each AdaBoost classifier has a detection rate and it eliminates some non-face images, right? So here, as you can see, the number of face images gets reduced, especially the non-face images are getting reduced when you are going for a cascaded approach. Now, this is the part of theory which I want everybody to know. Now, come to the part of understanding, right? Now, when somebody wants to do anything related to this, as I told you, you can always use Google Colab. or you can use your Python codes. There are a lot of Python codes with respect to face detection. I will show you one. I will also share you that. It's a very simple code. It's nothing very tough, but you should know that mathematics and theory, whatever we have seen, no, is working behind the code. That's a important thing that you should know. So let me open the code part. Yes. Yeah. So you can see here. So if you look at this code, what are we doing is we are trying to import a face detection code. So it is part of OpenCV. So this line says that we have installed OpenCV. Yesterday I told you, pip install OpenCV-Python. That means OpenCV is installed. So I'm importing OpenCV library. The next is I'm calling a cascaded classifier. This classifier will use a face detector.xml. What is this face detector.xml is? We have told that when I give a face, I can extract the features and the features are learned. Now somebody would ask me a question. If there are learned features, right, where is that learned features? Right, that feature should be somewhere available. No, that features which are learned is actually available under an XML file here, which is face detector.xml. Okay, it's available under an XML file called as face detector.xml here. Now, somebody would ask me a question. Okay, you have trained with 100 faces, but I have got 100 faces from a different country. Can I use that faces also and train? Yes. That case, you have to go and train and recreate this XML file. That is also possible. Please understand, that is also possible. That means you are recreating your face detector.xml file, right? So what is there in this face detector.xml is it has got the face images trained. That means features of the face images are being available, right? Now you go to the code part. We are loading that XML file. Then we are giving a test image, right? So since we are talking about test images, training process, again, please always understand, if you have 100 images, you should have 70% for training and 30% for testing. That means with 70 images conventionally, you should have trained your model to create an XML file. So you can give 30 images or one by one image you can give to check whether the face is being detected correctly or not, right? Then next is here we are using a method called as detect multiscale. What is the use of this method is, as I told you, we want to draw a rectangle around the faces as the face image is being provided, right? So for the X and Y height and width, right, of the given faces, I would like to draw rectangle around the face. Finally, I want to show the face image. The face image is face detector.png, right? So this is the code part. Now let's go to the execution part of it. So here, okay. One second. Okay, so here, let's open the code folder. CD face detection. Okay. So here we will take one more folder here. Yeah. Okay. So here, as I told you, that's a pre-trained XML file which has learned the features of the face image. There's a Python file. There's a test image file that we are giving, right? So we would like to see the faces are detected or not. So it's at one part I given one of the face detection image to check whether I'm able to get an ROI, right? That's a face detected output is coming correctly or not. One second. So this is a face image. So I'd like to see whether the face is detected correctly. I'm getting an ROI around the face or not. So let's go here. So let's run the code. Python my face detect.py. right? So what's happening is now it's taking the image as input. It will find an ROI, that it will draw an ROI around the face image. It will recreate a face detected image. Okay. Now this is a face detected image that's got created. So you can just double click and open and see. You can see face being detected correctly, right? Okay. So this is where you are taking only one face image, but it can be taken for any number of face images, right? As per your requirement, you can take any number of face images, and for each of the face image, you can actually check whether you are able to do a face detection or not. Right? Okay, fine. So the thought process is like we are interested in doing face detection approach, and we are also interested in knowing whether the face detection approach is working correctly or not, right? Now, the next question somebody would ask is like, what is that we should do challenging, right? When it comes to deep learning part, right? You are talking about deep learning, other side you are talking about face detection. So what is that we can do? That may be the next question from the participant side. So if you go to internet, okay, I'm just opening the, this is one thing that you can try offline. It's a working code. So if you go to internet, there are a lot of deep learning architectures that are coming for most of the problems, right? Somebody says I'm working on tumor classification. 2-3 years back, somebody would say that I'm writing code from the scratch. But now it's not like that. People are actually trying to create architectures, and the architectures are proprietary for the particular model. So in similar line, you will find an architecture called as FaceNet, right? You will find an architecture called as FaceNet. So this FaceNet architecture is being proposed by Google, right? And it's proved to be a very good architecture for face detection and recognition. You can see a lot of papers also which are using FaceNet, right? So my suggestion to the people would be is like, now you have seen a simple code of face detection working. So what you can do is you can take this code, like this code is a working code here, which actually does a face recognition part, right? You can take this working code and you can try to check the output of it, right? And more simple code of it, you can actually see it under this one, which is Geek for Geeks, right? Okay, this here also you'll find step by step of running a code on face detection. Okay, the only difference is this is built on deep learning approach. Okay, so I will put you this URL in the chat box. Okay, so use this URL and you can download and post it. Okay, so tomorrow's session, when we meet back, we will start with discussions on transfer learning architecture, and we will see how transfer learning can be applied for activity recognition. Okay, so that will be the discussion that we will take it tomorrow. And again, the implementations, we will execute it in Python and demonstrate it for your reference. And yesterday's session, there was one request with respect to medical data set. So to that participant, what I would suggest you is like, you can write me a mail. I spoke to the doctor. Doctor says that there are some ethical aspects in sharing the data set. If you can write me a mail, I put the mail ID in the chat box. So I will forward the mail to the doctor, and you can submit your official request for your research, and you can access the data set from the doctor, right? So that's was one query that was pending yesterday for related to medical data set. So that's it for today, and thank you so much for patiently waiting for the session, and I will take it back with transfer learning tomorrow. Thank you all.
Yeah, thank you, sir. Thank you so much.
Thank you, ma'am.
Thank you, sir. Thank you, sir. Yes,
Yeah.
sir. We'll meet tomorrow, sir. Thank you, sir.
Yeah, sure, ma'am. Sure. Thank you, participants. Thank you, ma'am.
So, dear participants, kindly fill in the feedback form. It's been posted in the chat box. And tomorrow we are going to listen to Dr. T. Sindhil Kumar on continuation of secure network analytics with deep learning and transfer learning. So, kindly join us tomorrow for the session. Okay. So tomorrow we are starting by 4 and we'll have the hands-on session. Thank you, sir. Thank you all. Thank you very much.